All right. Thanks everyone for coming to the October edition of the Distributed Systems Reading Group. This month we read the Edelweiss paper, which is essentially about distributed garbage collection, which doesn't sound very exciting, but is actually, at least I think, a really interesting paper. If anyone would love to give or would be interested in giving an overview of the paper, I'd love to kick off with that. Preferably somebody not from the Vision team, because we're doing a lot of stuff with this kind of thing. So if there are any volunteers.
Hey, Jesse here. I will foolishly fling myself into the breach. So they start with a language called Bloom, which I guess is basically a library that adds syntax to Ruby for distributed systems programming. And Bloom kind of restricts everything to objects that have local data structures and can pass messages to each other. And this seems to kind of emphasize leaderless, eventually consistent protocols. The paper doesn't say that, but that's my guess about this. So they want to come up with a way to simplify implementing things in Bloom by analyzing Bloom code and producing garbage collection code automatically. And they do this by kind of noticing a number of patterns in Bloom programs that they can then use to synthesize Bloom programs which automatically collect garbage. So for example, if you're trying to do guaranteed delivery by retransmitting messages, then they come up with a way to automatically acknowledge messages and then delete those from the outgoing message queue once they've been delivered. And things get kind of like increasingly complex from there as they recognize more complex patterns and compose these patterns together to come up with more complex synthesized programs. That's my understanding.
Yeah, thanks. Yeah, good overview. The only one thing I'll add in addition, a bit of detail, is the way that they're doing this storage reclamation, or I guess two things. One is they talk a little bit about how this is just all optimization, right? Like if we had infinite storage, we wouldn't need to do this, right? And two, that they're essentially making use of analyzing the programs and special properties in it to say, I know that I've gotten this far and that I will never need this fact again, therefore I can drop it, which is interesting from a garbage collection point of view, because it's not just saying I don't have a reference to it anymore. It's saying that I will never possibly in the future need this thing because of the properties of the query, which is kind of interesting. So, to kick off the discussion, as we often do, I'll ask my classic question: when would we not want to do this?
So one of the things they call out in the paper is that their techniques here are pretty catered to a subset of Bloom programs that only support monotonic operations. They do make use of non-monotonicity in the emitted code that they produce from these like higher level declarative specs, but there's a lot of constraints on exactly what sorts of code they're able to represent here. Obviously, not all data log code or not all programs can be expressed using monotonic data log. I know this example comes up basically every month here, but like the RGA CRDT is kind of a classic example of this. So I guess there's a little bit of opportunity there too in terms of probably applying the same sort of analysis that some of the other papers we've looked at, like the common collected consistency paper, to figure out exactly which pieces and like which slices of your program can be represented using a model like this, so that the compiler is able to determine where you can effectively make use of this sort of automatic garbage collection and where you might want to take a more hands-on approach.
Quinn, which CRDT was that? That's not
RGA, replicatable global array. So sorry, this CRDT is still monotonic. It's implemented using basically a DAG of insertion and deletion events that are rooted against where in the document they're modifying. And the way you evaluate those events in data log involves a lot of negation, in particular, because you're trying to find which nodes are like direct siblings of each other and which ones are uncles of each other and so on, which involves doing things like find the node that is at least two siblings away, or sorry, that is at least two siblings away, but that is not one sibling away. And that sort of thing is non-monotonic.
Cool, thank you.
So while we're talking about monotonicity in this, really specific use case, do you want to talk a little bit more about why monotonicity is so important to Edelweiss, Quinn?
Yeah, sure. Do you mean from like the perspective of COM?
From the perspective of why this even lets us do Edelweiss at all.
Yeah, where is it? So it really comes down to the fact that with a lot of the rules that they are applying here, they're trying to find the circumstances in which like a tuple that has been derived can never be underived using additional information. That shows up like when you're doing like negative set differences, for example. And if things were not monotonic in the ways that they require, then it's possible for results to like flit in and out of existence as new data is added, which means you need to keep track of like larger pieces of historical data so that you can kind of recover that prior state that's being that prior memory that's being reclaimed as more tuples are being added. And really a lot of what they're doing here is trying to find those invariants where like once something has been computed, it can never be uncomputed. And so anything that has been used in the derivation of that computation is no longer needed if it's no longer needed for any other computations. That's kind of a high level answer, but is that kind of what you had in mind?
Yeah, like maybe a simple example is if you have a register that is a last writer wins register, you don't need to keep around all the previous history on it. You only need the last version, right? Especially if you have, and they talk a little bit about logical clocks and things in there too. So, right?
I think some of their techniques rely on monotonicity too. Like, doesn't the range compression, for the range compression to even work, like you need to have monotonicity, right?
I don't actually recall the details for that one, but
yeah, the range compression is like so essentially like you're tracking sets of IDs that you you can reclaim the fact or get rid of it or whatever, and rather than like tracking every single message ID, you can say, okay, well, I know that everything between 1 and 5 is fine, so I can just like track 5 or whatever.
That's the part on the watermarks, and they also get into that with the epochs as well, right? For the dynamic.
Right, yeah, and I guess the monotonicity comes in there because if you need to split apart a range, you don't necessarily know where you can do so safely, like if multiple consecutive ranges have been merged together.
Yeah, exactly.
Since at that point, everything within their range is indistinguishable.
Yeah.
I think they specifically call out a case when they're talking about adding, like doing deletion. I think it was in the key value store. They're like, we can't really do range compression on this because like we're not like just counting our acts for consecutive message IDs. We're like, we don't know what's going to end up being deleted. So we like, there's not really anything to compress necessarily. And that feels like an example of a case where like the range compression stuff really doesn't work even though they've still got monotonicity. And so they have to break out. I think that's where they introduce the negative set difference stuff.
The technique that they apply there is also one that actually shows up in a lot of other data log implementations that are kind of outside of the Bloom lineage. I've seen this idea talked about a lot in some of the static analysis engines, where one of the ways that they try to optimize things, not from a storage perspective, but from an evaluation perspective, is by trying to pair like insertions and retractions together. Because if you have like a batch of updates and you can always like match up an insert with a delete, those can cancel each other out. Or if you have like an odd number of insertions, you know that it's going to end up being like an insertion overall once you combine all of those together. And that feels like a like CPU dual to the storage stuff that they're doing with the negative set or negative difference reconciliation.
Yeah, it reminds me a lot of, and I guess this is maybe a little off topic for this specific group, but remind me a lot of data log with negation, right? Like there's a direct parallel here, right? Of like when you have things that are non-monotonic, right? Then you have to start breaking things up into little sections and tracking at minimum the negative stuff, and you can never get rid of it, right? So I thought it was interesting that you can never reclaim, at least fully, the negative facts, right? Even if you can do, and compression and things like that on the positive stuff, you can never actually get rid of the negatives. So that will grow forever.
But just the message IDs for the negatives, right? Like you can reclaim the facts and the data, but you just need a marker to know.
Yeah, exactly. Like you can keep their hash or their sequence number or something like that. Exactly.
I guess that is to say that you could probably have like a CRDT, which represents a set, and it could still technically have 0 elements, but it could just have a million insertions and a million deletions. When you guys usually think about a lot of these CRDT implementations, what kind of like pattern language do you guys use to talk about them and like manipulate them algebraically to, I guess, know what they do and know what their differences are between different implementations or different specs, different properties? I'm kind of new to the space and a lot of the literature. I'm also really interested, Quinn, in what you said about the learning about the lineages of data log-esque programs that don't come from Bloom. There's a lot that I don't know about that. That probably strikes on the fact that there's a lot of interesting research veins that I don't know about.
Yeah, there's a lot of really fun stuff out there. It's kind of been my experience that the data log work kind of falls into 3 camps. There's all this Bloom stuff that we've been really excited about with this reading group. There's the static analysis stuff that you see with like Inca and Souffle. Souffle has a lot of really wonderful papers out there about like really efficient data structures and stuff. And then there's a lot of the really cool like query language database work from the 80s and 90s that I think lays a lot of the foundation. Separately, there's like answer set programming and things like that, which is more like logic programming rather than query languages like this. But feel free to reach out afterwards. I can send you some cool resources.
Cool, thanks.
Answer set programming actually does, as Brooklyn was mentioning, how negation kind of throws a wrench in the works. Answer set programming does some neat stuff with dealing with negation. So the idea of answer set programming is basically you're using a modified Prolog, a logic programming language, to like represent your model to the to what is effectively an SMT solver. And one of the steps that they do as they're like generating the like low level first order logic query for the SMT solver to solve is they go through and they like evaluate all of the negations and try and effectively cancel them out or just get rid of them if they can, so that they have what is largely a positive program to evaluate, which is neat.
Sorry, I realized I forgot to answer the first half of your question, which was how to think about these different types of CRDTs. And I also think there's kind of 2 answers there. And I think Brooklyn might have a lot to add here too, because we've kind of developed our own internal pattern language for thinking about these in the context of data log. But like the more general answer is that you have this like distinction between op-based and state-based CRDTs. That's probably what you've come across in a lot of your research. But with this data log stuff that we've been doing a lot of, most of what we are thinking about is how to represent these CRDTs as these graphs of events with dependencies between them, like the RGA one I mentioned a few moments ago. And in thinking about them that way, a lot of the way that Brooke and I talk about this stuff is kind of as if they are like the database equivalent or distributed systems equivalent of like an AST for a programming language. There's like a couple different species of graphs that these structures fall into. You have things like RGA, which are these like really like deeply nested structures that encode a lot of information into their shape. But then you have things like counters, for example, which are a lot more flat and maybe a ton of events rooted under some common entity root, each representing an addition to a set, for example. There's cases that, like if you're dealing with like last write or wins registers, where you may generally have a very narrow but very long structure that has a couple different branches that occasionally like branch off from each other, but then merge back together as reconciliation happens. And really those three categories are where we've been finding that most of these CRDTs fit. And interestingly, a lot of them seem to have fairly similar like performance characteristics and just like semantics, I guess, under like data log style evaluation. There's like really deeper like AST types are the sorts of thing that I think something like Edelweiss has a lot more problems with.
I'm just going to jump in before we go to Philip. So in terms of evaluating these data structures and just generally systems like this, right? So any CRDT needs three properties. It needs to be idempotent, commutative, and associative. And if you think about it from the
join semilattice,
it's a meet. Well, it's only a joint semilattice actually. The meets, right? So they just have to converge. It doesn't necessarily have to come from the same spot. So as long as you have any of those, it's actually completely fine. There's two hard things, right? One is proving convergence is actually really difficult and sometimes extremely subtle. So you'll look at something. And you even have experts, right? Like Mark and Kleppman, who, and this is the one that's been getting cited around this group recently, who was teaching a class on CRDTs, looks at something and goes, this obviously converges, and then spends a couple hours trying to prove it, can't prove it, and turns out it doesn't converge, right? So it's like really frustrating sometimes and really super subtle. And then also they're often really easy to make and to design new ones, but they don't necessarily behave the way a user would expect them to. So getting the user expectation right is really difficult sometimes, right? Because there are lots of things that have these three properties, but that maybe will pick the wrong data during a reconciliation, right? So when we're looking at these things, and you can always represent a CRDT as a graph, as a DAG, right? You can convert any of them into the style. There are sometimes performance trade-offs. So if you have something like a counter, the way that you think about this as a DAG is just that it's like the degenerate case, right? If you have one root and then a whole bunch of leaves off of it immediately, right? And you just keep adding leaves. And you can say take a count of the number of leaves it has, right? And that works really, really fast because it's, you can divide and conquer, you can do all these things. If you have this really long structure, and especially if it has links between them, causal links between them, you often have to walk big parts of this tree or big parts of this graph to do anything. And so it has all of the right properties, but you have this performance trade-off. It becomes Byzantine fault tolerant, but you have to walk more of this and pull more facts down. Unlike some other algorithms where you don't have to do any of that at all, right? So last week or so, we had a sort of a not part of this main series, but part of the same group, I guess, where we looked at Katara, which is a synthesis for program synthesis for CRDTs. And one of their points was like, well, we don't want to have to do all of this, grab the entire data store to work on it, right? Like we want to do smarter things. But then there's other trade-offs, because now, you know, malicious nodes can really throw a wrench in the works, things like that. So which is the really long way of saying, we've identified these simple species of CRDT and these shapes that work for our purposes because we're slightly paranoid. But there are lots of cases where you'd want to do something in a more trusted environment that might have better performance characteristics, or that behave in a way, you know, designing the way that the user expects it to behave is sometimes difficult. Philip, you had your hand up.
Yeah, basically you've covered most of the things I wanted to say. Essentially, I wanted to bring up Katara as well, and something they wrote in there that I don't remember exactly how they wrote it, but they were like, we're using state-based CRDTs, which are essentially joint semi-lattices, and operation-based CRDTs can be derived from state-based CRDTs, according to those authors. So I think
and the other way around.
Oh, okay. Good. So yeah, I personally feel like joint semi-lattices and state-based CRDTs are like the framework to think about CRDTs for me.
And the reasoning, Quinn, for why the other way around is intuitive is because all state-based semi-lattices are just partially folded structures. Yeah, they're just partial folds from the original kind of like list of messages that's held. Or not list of messages, but like whatever the set of all messages that's contained in the op-based CRDT.
Yeah, exactly. So if you can take the operations and basically bundle them up in like an envelope representing an as of yet unapplied operation along with the dependencies that need to be fulfilled for it, then you can impose that ordering and evaluate them.
I thought that was kind of interesting about the Edelweiss implementation, about saying, how do you provably know that you don't need this message anymore? And maybe if you can show that you can iterate some of those operations that you get in messages into a fixed point contained in a state that's passable, you know that you have like a snapshot that's distributable, or in which you can recover your program in the case of like crashes or something like that.
Yeah, I think
that's
sorry, go ahead.
kind of the. Oh, I was going to say, I think that's like another way of phrasing sort of the core idea in the paper, which is actually it's a nice sort of short version of it, right? Which is we can look at the query. We can look at when we're going to hit a fixed point, right? Which is the output, and say this fact is never going to end up in the output, and I can prove that by showing that it will be negated immediately, or it doesn't show up in, you know, we're only going to select things that have a certain attribute on them, and that's not this one, or whatever, and then we can clear it, right? Yeah, absolutely. Quinn, did you have anything else, or should we?
So that was almost exactly what I was going to say. I was going to mention, God, what's the paper you sent me a week or two ago from like the 80s about what happens when storage is free?
What happens if mass storage is free?
Oh, okay, that's basically the title. It's Copeland from a couple decades ago as optical disks are taking off. Imagining like a world where storage is free and we no longer need to delete things, and what that means for distributed systems and databases. I thought it was funny that like optical disks for him are like the aha moment, like, oh, we're almost there, storage is almost free. But one of the really interesting points in this paper that I think is kind of touching on what you were getting at is that there's this duality between rolling up like updates over an interval of time into like one snapshot or checkpoint that represents their state after application, versus just keeping all of those events around forever in a way that lets you like replay those arbitrarily. And that like both of those have slightly different benefits in terms of the storage characteristics, but with the lower storage from rolling things up into snapshots, you also end up with like greater risk of data loss and like less flexibility in terms of exactly which data you can recover in the event of either data loss or needing to put together like an audit trail or anything like that. And there's no data log in that paper. It's definitely a very high level paper. Like it's from a couple of decades ago. It's more of a think piece than anything, but there's definitely like a shared train of thought there in terms of like imagining what these systems look like if we can start to just view everything as this like unbounded log of events that just keeps growing and describing how our system changes in time. And yeah, I don't really remember where I was going with that, except for the fact that I think some of what you're saying fits into that framework a lot.
Brian.
Well, I had a question about the paper, which this whole idea of like checkpoints and maybe kind of like leads directly into it, or leads nicely into it. In the reliable broadcast section, they discuss this idea of dynamic membership and introducing epochs. And the way I understand it is that like the epochs create kind of like a membership balance for safe reclamation. Like you know, we can say we know we have this fixed group for the state, and that's going to make it safe to like reclaim things over the state. But the thing I was wondering about that is like, do we need to get to the point where things are consistent before we can move on to the next epoch? And does that mean that like a new member that wants to join might have to like wait for like a couple minutes or 10 minutes or God knows how long before they're actually able to join into the network?
Yeah, and that shows up in a couple other papers in covering similar topics under the term causal stability, I believe. You see this a little bit if you're looking at logical clocks, when you're thinking about how to do like memory compaction, especially for like, CRDTs, for example, where if you have these like logical clocks, like if you take like a vector clock, for example, that keeps track of the like latest observed version from each node for a fixed membership. Once you end up with some like abstract vector clock that is less than all of the other vector clocks, you know that that represents like a lower bound of what people have seen. And so you can compact everything to that point. But that does require like being able to act under the assumption that at some point everyone will communicate and like share their progress with each other, so that you can have that like measure of how far through the event stream all of the nodes are.
Yeah, right. Like what if one of the members in the fixed membership group goes offline, or there's a network partition or whatever? Yeah.
Or it's a dynamic group, which like you said here, like they deal with that dynamicness by having these epochs where you like constrain essentially like the amount of time that nodes can go offline, or the period between nodes being able to join the system. Does that answer your question? So,
and just to extend that a little bit, if you remember from the FLP paper that we looked at a month or two ago, right? It says that there's no general solution to this problem, right? What they've essentially introduced is consensus for some range. You have some synchronous protocol, right? That says, for these members, we agreed on this thing and we're committing this, right? And we can do that by majority vote or by something, or by deciding that we're only going to do, you know, whatever, 100 writes or something, right? But you might have somebody who was under a network partition that was making a bunch of updates, and we're going to drop their events or try to get them into the next epoch, but they're not like confirmed. So you have this really, I also agree, this was super interesting part of the paper, right? Where you have this interplay between eventual consistency and a synchronous protocol. Kind of interesting. Yeah. Jesse, then Zishan.
Side note, yeah, MongoDB has this problem. We basically implement Raft and store a configurable amount of log. And if a node is offline so long that it has failed to replace some of the events before they are trimmed from the majority's log, then it's kind of in trouble and needs to do this whole resynchronization process in order to begin catching up. I was curious what the group thinks about the Edelweiss approach in general, because it's like a compiler optimization. You write some code in a kind of high level, and then the compiler analyzes it to try to find optimization opportunities. In this case, opportunities to reclaim storage. But sometimes optimizations are nice but not required, like a C++ optimizer making your code faster. And in this case, these optimizations are basically required. Otherwise, your system will eventually run out of storage and die. And that seems like a pretty bad consequence for a secret and implicit property of the system, where you have to know whether Edelweiss will pick up on something that you're implying at it. And sometimes you can hint at it, like calling a data structure sealed to indicate that it won't grow anymore. That allows optimizations that might not exist otherwise. I don't remember if the paper mentioned something like this, but if I had a system like this, I would want it to actually verify whether any data structure will grow infinitely or some data structure will grow infinitely before I decide to just trust the optimizer to do the right thing and send my code off to production.
I have an answer. I'll give other people a chance.
Oh. I really like the compiler model for this sort of thing, although I don't have a whole bunch of hands-on experience, so perhaps it doesn't fit. But I find myself, at least in the cases where like this compiler model comes up, because the paper we mentioned, the Katara paper from the bonus thing last week, also uses a sort of compiler model, and it feels like lots of the current distributed system stuff is like, by analogy, working at an assembly level where you're working with super low level primitives to make everything work. And that's fiddly and prone to subtle errors. And moving towards these sort of compiler approaches feels like moving to like you said, like higher level languages that give you like bounds on what you can write in order to restrict the sort of space of what's allowed to prevent you from like shooting yourself with a foot gun. And like you said, like some optimizations are just sort of nice to have. But one thing I thought of as you were mentioning that was C++ has like there's optimizations that are nice to have. But one thing that it lacks is you don't get very many memory safety guarantees unless you're very careful, as opposed to Rust, which like part of the quote unquote optimization that it provides by its framework of ownership and stuff, like gives you memory safety. And it seems like you can get similar guarantees with similar approaches in a distributed system context.
So you touched on a lot of the things that I feel about that question, but I really liked what you said about the way we write these systems kind of being like assembly for distributed systems. And there's a quote I really like from another Peter Alvaro paper called Abstracting the Geniuses Away from Failure Testing, where he basically says that distributed systems relies on a super user's ability to interpret how a distributed system employs redundancy to mask or ameliorate faults. The ability to recognize the insufficiencies in these redundancies. In other words, human genius. And I think that kind of gets at one of the problems with the way we currently write distributed systems and the assembly point you made. Things like writing programs that converge or that are guaranteed to terminate or that don't run out of memory are basically like impossibly superhuman tasks that some people are able to do, but it's such a small fraction of programmers. And so yes, it's a little bit scary relying on a compiler to make those optimizations for you, but I don't think we're doing a very good job of it ourselves in the first place. And once you have a compiler able to do that sorts of analysis, it's also able to detect when that analysis doesn't apply. So not only can it tell you how to implement a data structure efficiently or do that for you, but it can tell you when what you're trying to do does not fit into that framework in ways that you might not recognize yourself as a programmer doing this sort of work manually. So I'm a huge fan of the Edelweiss approach, but I also think it's kind of exciting on a meta level, because when we look at declarative programming, usually we think of it in terms of like describing what we want to do, and then the compiler finding the way to do that like most efficiently from a performance perspective. But I think approaches like Edelweiss show that it's not just performance we care about, it's other system properties and even like user intention properties that we can have the compiler model for us. And I think that there's a really exciting world out there where our compilers are helping us with consistency and garbage collection and like conflict resolution from like a user interface perspective, and just like taking all of these really horrible problems that we don't know how to solve now and giving us the tools to work with the computer to solve them more effectively. That's kind of my rambling answer to your question.
And just to tack on one extra piece to that, and drawing a direct analogy to programming languages, right, over the past 60 years, I guess, it's true that humans are often really terrible at this kind of analysis and optimization. But there are definitely cases where you'll want to hand optimize something, but that's not the 98th percentile of all systems, right? So I think the argument, at least my argument for it, is it should be automated as much as possible, except for the really performance critical stuff where, you know, like if you're building a small app for you and your company, the garbage collector or Edelweiss or whatever, plenty. If you're building something at, you know, massive scale and getting a, you know, a 2% improvement, or heck, a 10% improvement is going to save millions of dollars. Amazing. Go in and write some custom data structures, right? But usually, and there's always, every time that we introduce a new layer of abstraction, people worry about like, well, but you're taking my tools away. I would love to see a framework that lets you do both, where you have a high level layer and then something lower, like an intermediate representation or something that you can still plug into. Just because I see that there's a whole line of hands up right now. Zishan.
Cool. Yeah, I won't take up too much time with all the hands, but yeah, so obviously there's a lot of conversation from Jesse's question, which is really good. Of course, similar like in Mongo, like even though we didn't do Raft or anything for React, we went through a lot of the same issues that I think is like, how do you actually deal with eventual consistency when things are in a coma state, right? Fully offline for a long time. I think that was a good mention. The thing, I guess, to get to your question, I actually think the tension here, there's two tensions. One is in systems like this that or like the Katara paper, which is synthesizing code from, you know, sequential types. I think the one issue is we haven't done a good job. I say we as a putting my type systems hat on. We haven't done a good job in the perspective of actually like what are the right kinds of ways to identify type systems, now that you write things as you would, you know, kind of that like verification that's not implicit but actually tells you what's wrong with what you're writing, and give you ways to express types at a very high level for these kinds of things. You know, there's been some work obviously like session types and these other kinds of things, but they don't get to this level of things. And actually a lot of these researchers have tried and kind of said, screw it, let's go for these other pieces. And I think the other one is, you know, maybe a lot of people don't like the implicit nature of this. I mean, you do look at the bigger companies, what they're going to do is start looking at model checking, you know, symbolic execution, and a lot of the work that's come out of Facebook with Infer, Amazon with the stuff that they're doing in Rust today, which I was just listening to a podcast on their SOCC paper, I think from 2021, for lightweight verification and formal methods. So I think that's kind of the tension here. How much do you want to give it for a programmer to kind of write something and get kind of reasoning and optimization out of it, versus no, I'm actually going to write, I actually have to write a model. I want an easy way to model check this. That's what I want you to give me instead. And I think that's really a lot of the tension the systems world goes, right? Where some people are thinking at this kind of hydrologic and like language level, or like bits of language and synthesis. And now like a lot of the systems land is like, no, just give me the tools so I can reason about what I'm doing more explicitly.
Awesome. Yeah, I mean, could not agree more. And I saw lots of heads nodding along. I really love the Bloom work, but I think there's so much more that could be done in this direction, right? Quinn and I were at a conference a couple of weeks back, largely about distributed systems and databases and stuff, and got to chatting about like, well, what would a language that's based on these structures, like a general purpose language that's based on all of these structures and having global distributed memory actually look like? And I think it's an underexplored area, right? And especially as things get more interconnected, I think there's gonna be lots of interesting space there. Cool. So Zishan, you still have your hand up. Did you have more, or should
No,
we?
I'm good. I'll put it down. Sorry.
And sorry, I'm going to completely butcher this. Asakamar?
Yeah, it's up, by the way, but thanks. So I'd argue that these systems actually exist and they're not very hard to use. So for example, like when I build a lot of CRDTs, it's often the structure is like a conversation with your compiler where you're constructing this generalized algebraic data type, and you're working alongside the compiler to actually prove properties about the structure of your GADTs. So like you have law checking where you go in and you prove like, hey, is this thing a semigroup? And you prove that it's got your semigroup laws. And then you prove that it is a commutative monoid. And then you prove all the way up to a joint semilattice. And it's actually a really, really nice experience to work with. So it gives you the ability, like, for example, for these like reference paper implementations where they're saying, hey, we need to do message passing and we need to do provable snapshotting, right? I can just refactor that into saying that I have an algebraic data type whose messages, who's like, it's a sealed, like you can do things like showing that it's sealed and that the message space doesn't grow. You can show that, you've got some messages that you need to handle for regular message passing, and then you've got snapshots, and another thing that's really nice, and one part of research that I really enjoy looking at is like looking into dependent type theory. And in languages which have dependent types, you can do things like further prove properties, right? So then you can prove like the eventual termination of the merge operation in your join semilattice. And that's really nice because then you get structural properties about how your CRDTs perform in your programming environment. And like the delta between understanding that this thing is going to work and having the proof of the work is just right there. And it's a really, really freeing environment rather than having to like test so much in the wild.
Amazing. Yeah, I think you're going to get a lot of pro-dependent type people around here. Question about that, because obviously dependent types are, at least today, really aimed at, I'll call them like expert programmers, right? I really like them. I've used a lot of Idris. I played around with Unison, but there's still like this element of you have to get to the point where you can reason at both the type and term level, and like you get a lot more help from the compiler and the tooling, but it ends up being really specific to like this kind of a system. Do you think that there are ways that it could go further and really start to say like, hey, by the way, you probably, if you add this to your type, we're going to start enforcing nice properties for you, things like that? Like, do you think we could take it further?
Yeah, I do think it can be taken further. Like one thing that I'd, it's kind of like a little bit fanciful, but I was always really frustrated writing sorting algorithms because I'm like, these literally have the same type. Why aren't they the same? And like, I couldn't understand why they're not the same. and being able to express them via dependent types, they carry along these extra bits of information, which are proofs about their asymptotic complexity. And they're literal physical tokens that get passed around in code as little mechanical proof assistants. And it's just a really, really nice programming environment. There's also this really nice paper and a set of talks. I think her name is Stephanie Wyrick over at UPenn, talking all about how to write, how to make a nice system for developing red-black trees. And one of the hard parts is like showing that the balancing operations are correct. And it's nice because you can see these little tokens actually get passed around, and you get nice help from your compiler about like, hey, you didn't prove that this operation that you're trying to do in the right has provably less complexity than the thing on the left. Go try something else. And I'd much rather have that feedback there than I would writing a bunch of tests and then scratching my head for like 3 days and figuring it out later.
Yeah. Have you seen any of the work on, and sorry, this is a bit of digression just because there's some PL geeks around here. The type-directed program synthesis stuff that uses dependent types as well.
Can you say more? Maybe I'm just not familiar with the naming.
So you can give the system a type, maybe even with some holes in it, and no program, and it'll say, let's try some programs that match this type. And it'll start to synthesize for you a program out of known components, or sometimes using fancier techniques. Say like, well, you've given me the type of a red-black tree. Let's just start plugging in red-black trees and see which one's the most efficient for the rest of the context that this code's being situated inside, or giving the programmer, hey, here's 3 options. Which of these looks right to you? Or none, right? Have you seen any of that in a distributed systems context with like in Unison or something like that?
Not in a distributed systems context yet, but I know a lot of people are familiar with it. And yeah, stuff like that, it feels like mechanically when we want to say abstracting the genius away from programming or from distributed systems programmers, I imagine that that's the mechanical thing that we're doing in service of abstracting genius away.
Amazing. Just as we're slowly running out of time here, Mark and Swan.
Yeah, I feel a bit embarrassed. A lot of this is beyond my knowledge. But really, the whole discussion about high-level language and I see the value of having the high-level languages so we can give intent and let the computer find optimization. And the low-level language where we can try new optimizations that the compiler doesn't yet know about. And I think there's a whole dynamic of what we'd like to do is make this block of low-level thing and tell the computer, well, these are the properties that you can reason about for your next optimization. But that requires what kinds of properties we're already thinking about. And a lot of the high-level languages are working on different axes. Like we're thinking about the ability to garbage collect or to manage ownership in Rust, the ability to manage distributed characteristics, the ability to manage CRDT characteristics. These are different feature sets, and they're not totally independent. They're obviously very tied together, but it's also true that people build high-level language to focus on expressing as intent one of these characteristics generally. And I wonder if how possible is it to mix different things in language consideration. Purely speculative, I'm thinking aloud, but it's what I'm seeing is all these systems that explore this thing or that thing and this thing separately as high-level constraints. And I totally believe in thinking high-level because most programmers, I agree, cannot reason about this correctly. But being able to be told the back and forth, well, this high-level structure translates to that. Yeah, it's very important. Rich polymorphism, Zishan, yes, I agree. That's something I've heard that Julia does really well because of, well, any language that has multiple dispatch in theory. But Julia, it seems, accomplishes it well in practice from what I've heard. I don't have that much concrete experience yet. But anyway, I just wanted to throw this as the programming language question we're all asking in a way.
I like some of the points you brought up. You said we need to think about what properties we want when building these distributed systems. And you also said that you like to think at a high level. And that's one of the things that I really enjoyed about the Katara paper, because under the hood, it's doing a lot of this like really fancy verified lifting and program synthesis and things like that. But as an end user programmer, you're not writing a data structure and saying this needs to be like an abelian group in the category of the endo functors. You're saying this is a data structure that supports an insertion and a deletion operator. And I would like deletion to take precedence over insertion as a very high level property that kind of maps to the user intention surrounding the code and what it's meant to be used for. And I think it's really elegant the way that they were able to take all of these different similar but slightly different CRDTs and distill them down to a couple very high level properties that you can talk about and like very high level and like end user accessible ways, like operation ordering and idempotence and so on. So I don't know if that's a little bit what you are talking about with what sorts of properties do we need to define these systems, but I think that there's a lot of really interesting stuff to explore there.
I think going back and forth, and the back and forth, you know, Brooklyn's between the high level and the lower level. And Brooklyn spoke of, can I dive into this block unsafe, yada, yada. But then I'd like to be able to take this block unsafe and say, oh, by the way, I think it has this property, that property, that property, so that the compiler can reason about it. But we don't, but different properties according to different property spaces, which may be independent.
And you saw that there too, where like the end user is dealing with idempotence, but the implementers of Katara are still thinking of things in terms of semi-lattices and so on.
Yep. No, it's very fascinating. The other last quick thing, composability. Like CRDTs compose, I'm seeing that there's composition in Edelweiss. I think this is going to be important no matter what. And again, do those different axes of optimization compose well together? No clue. Over.
Yeah, historically CRDTs didn't compose directly, right? Because let's say you have one nest inside the other and they might have different semantics, right? It's like there are all these edge cases. People exploring things like, well, what if we just treat these all as a particular, in the same framework has led to massive gains in composability, which is really great. We only have 3 minutes technically left. I just want to queue up for Quinn. Since we're talking about really like end user programming of these systems and taking all the really hard parts out, but still letting people, you know, customize the thing to their use. You know, there's been a bunch of attempts at doing things like, well, just only supply me the merge function, things like that, right? Just like the little part, and then we'll handle the rest of the syncing and the, you know, the figuring out where, you know, that these two are in conflict and all these other parts. Turns out that it ends up in the general case being actually pretty tricky. Quinn has been thinking a little bit about user-defined functions. Do you want to sort of just like, and I know I'm putting you on the spot a little bit, but just like give some thoughts about that?
Yeah, for sure. So as some of you know, we're very interested in data log, and we're kind of using data log as almost like a lambda calculus for distributed systems. So allowing people to, on the front end, write views for their like React application, for example, that end up compiling down to data log that then get incrementalized so that they can have these like automatically convergent views over shared data that they can incrementally evaluate. One of the challenges there is that data log, while very expressive in some ways, cannot represent all programs. In particular, it tends to really concern itself with things like set membership and set intersection and joins and things like that. Once you start wanting to actually perform computation over the data, data log doesn't necessarily have a lot of ways to do that. So what a lot of implementations of Datalog do is allow you to have user-defined functions where maybe you literally write like a Haskell function that you stick into the body of a Datalog rule, and then that modifies the arguments somehow to produce a new fact in the head. There's a couple problems with this. Programs won't necessarily converge if you have user-defined functions. Really trivial example, natural numbers, a successor function just adds 1 to whatever number it's given. That's going to return a new natural number every time. So there's always a new natural number for any other natural number. So if you like recursively call that, that program is never going to achieve a fixed point. In our case, we can do something really clever because we are working with data across time. And so there's this dimension along time in which we can stratify the evaluation of a program. So if it's not possible for past states to access future states, for example, that gives us a little bit more control over what sorts of things we can do inside these computation. But then more generally, user-defined functions need to be ideally idempotent, especially like pure. You don't want side effects really as much as possible, and they need to be terminating. That's really difficult to do if you're treating Datalog as like an assembly language to be called from lots of different high-level DSLs, because now you either need to define your own VM for these user-defined functions that only supports the capabilities that you want these user-defined functions to have, or you need to do a lot of validation in those higher level DSLs. So something like Haskell, for example, can more easily capture the idea of a side effect-free function that you maybe use as a UDF. But if you're compiling to that same underlying query engine from JavaScript, for example, that's much more difficult to do. What if you write your own VM? Now there's a lot of portability issues. There's also expressivity issues, there's performance issues. That's like a lot of implementation overhead to support your own VM for that sort of thing. But we have WebAssembly. So what if you basically stick these WebAssembly VMs into your Datalog rules as these user-defined functions? You disable any sources of non-determinism. So you do like canonicalization, you disable shared memory, etc. Now you have these like pure functions that are portable across implementations. You can share UDFs across different languages. And because they're side effect free, you can also memoize them. So within the evaluation of a rule, if some UDF is called multiple times with the same inputs, you can memoize that and cache it and not perform that computation again. That's obviously something that you can do in a higher level language too. But going back to the abstracting the genius away from programming, that's the sort of thing that users need to think about, and that people usually only do once it actually becomes a performance bottleneck and they've done profiling and realize that's a problem. But if you're able to automatically find the pieces of your program to which that optimization applies, make use of it and get those optimizations for free, then that just completely removes that burden from like the cognitive load of the programmer. Let's see, is there anything else I'm missing there? I feel like there is. That was kind of a whirlwind tour. Is there anything else that comes to mind, quick?
No, I think that touches on the major points.
No, there's a really fun part. Meta UDFs. So in our case, our query engine is intended to operate over a content adjustable store, such as IPFS, which means that everything has a consistent and stable identifier with its content ID. If you store WebAssembly blobs inside a content adjustable store, they have a content ID too, which means that if you're able to reference UDFs by their content ID, then you can have facts in the database that reference content IDs that you can load into the Datalog rules at runtime to get almost like Datalog metaprogramming. And where this might end up being a really interesting thing to explore is through like a lens library that you implement for Datalog, where maybe you use WebAssembly to implement lenses between like different JSON schemas. You can stick those lenses into the content addressable store in a relation that associates them with the SIDs of the schemas they convert to and from. Then you can take like a Project Cambria-like approach, where you build this graph of all of the lenses in your system, including the schemas they translate between. And then if you have something of schema A and you need something of schema C, you can try to find a path from A to C through these lenses. Each edge on that path corresponding to one of these UDFs that translates from one schema to another along that path, and then apply all of those at runtime to basically automatically translate between JSON of different types. None of this is implemented in my system, but it's kind of something I've been thinking through, and it's a little bit scary because there's a lot of power here that may have implications I haven't considered yet, but I'm really excited to explore it some more.
And maybe to separate that out from the stuff you were talking about previously. So there's the WebAssembly version of this, where people can write arbitrary things. If you express those same lenses as Datalog, you can apply much smarter compiler passes to it that end up being much less lossy when you're pushing data through it, right? So the example that I gave recently was if you go from A to B and you drop a field, and then from B to C and you add a default to get that field back, we want to just get rid of this middle transformation. If you're using something like WebAssembly, it's not rich enough without like really heavy analysis to know about that. But if you're doing this with Datalog or with a query language, you can much more simply understand what's happening. Quinn referenced Project Cambria. Really nice write-up about that from Ink and Switch. Would recommend. We are well past time, so I'm going to turn off the recording now.